Okay, now we're going to discuss natural exponential functions. A natural exponential function is a special function that you see a lot for growth applications. And the natural exponential function is the function f of x is equal to e to the x. Now, even though we don't write it in there, we can assume that there is a coefficient of 1 in front of that e. Now, e is like pi. It's an irrational number, just like pi is 3.1415, and it continues to go on forever without any specific pattern. E is also an irrational number, and we estimate e, just like we estimate pi at 3.14, we estimate e at 2.718. So my leading coefficient for the exponential function, the natural exponential function, is 1. And my growth factor, my b, for the natural exponential function is e, which is 2.718. Now, you can find your e button on the calculator. If you look at your Texas Instrument calculator and you look to the left of your 4 button, there is a button that says LN. And then right above that in a different color, because you would choose second option, it says e to the x. That will be your natural exponential function button. Okay, so some things about the natural exponential function. Let's see what this graph looks like. Because it's an exponential function, and my leading coefficient is 1, so that's going to be my y-intercept. So it's going to cross at 1. And this is an exponential function, and because e is greater than 1, which is my growth factor, it's going to be an increasing exponential function. So it's going to look like this, just a rough sketch. It's still going to have a horizontal asymptote at y equals 0, unless, of course, you start vertically shifting it. It's going to have a y-intercept at 1, of course, unless you start vertically shifting it. And then there are no x-intercepts. My domain is going to be minus infinity to infinity, because if you look at our arrows, right, this arrow tells me I go down and to the left forever. And this arrow up here tells me I go up and to the right forever. So I know my domain is going to go from minus infinity to infinity for my range of x values. And my range is going to be from 0 to infinity, because we have this horizontal asymptote here where it starts at 0 but doesn't actually touch 0, I should say. It keeps getting closer and closer to 0 but never actually touches 0. So since it never touches the x-axis, it's going to be anything greater than 0 and up to infinity. Okay, now, if I look at and I compare e to the x to 2 to the x and 3 to the x, since e is between the numbers 2 and 3, if I were to graph 2 to the x might come up like this. And 3 to the x might come up like this. Because 3 is bigger than e, it's going to jump up a little bit faster. And since 2 is not as big as e, it's not going to jump up as faster. So e is going to come up in between 2 to the x and 3 to the x. They're still all of them are still going to cross at the y-axis at 1, because they all still have a value of a for 1, but they're just going to grow at different rates. And 3 is going to grow faster than e, and e is going to grow faster than 2. Okay, so now let's start into some applications of exponential functions. This first one is a nice, easy one to get started with. It talks about 2 forests, Forest A and Forest B, and they're describing the growth of the forest with a formula. Forest A has the formula 111 times 1.021 to the power of t, and Forest B has the formula 85 times 1.024 to the t. And so if you plug in t represents the number of years that have passed, then you're going to get out the number of trees that the forest has. Okay, so in part A it says, which forest population is growing at a faster rate? So we want to look to see, since the faster rate has to do with the growth factor, we want to look to see which one has the biggest growth factor. So forest B has a growth factor of 1.024, and forest A has a growth factor of 1.021. Now between the two of them, the growth factor for forest B is bigger. So forest B is going to grow faster. For part B, it says which forest had the greater number of trees initially. Well, when we look at the graph, when t is equal to 0, we want to look to see what the corresponding y value is. How many trees do they have? So when we look at that graph, what we're looking at, the initial value would be the y-intercept, which is our value of A. So our initial value is going to be the value of A. So if I look at forest B has an initial value of 85, because that's what's in front for our coefficient. So forest B starts off at 85 trees, and forest A starts off at 111 trees. So forest A, even though forest B is growing faster, forest A started with more trees. And in part C, it says, assuming the population growth model continues to represent the growth of the forest, which forest will have the greater number of trees after 50 years? So we want to see how many trees each forest has in 50 years so we can determine which one has more trees. So I'm going to plug in for forest A formula. I'm going to plug in 50. And raise that to the power of 50. That's my t. Now, typically we use an x there for our independent variable. We usually use x, but in this case, they're using the letter t because it's t for time in years. But just be aware that when you put it in on your calculator, you still want to use your x button if you want to go to graph this or anything like that. And then also keep in mind too, if when you're working on your online homework, if the question is asking you to use independent variable t, but you plug in x for your answer, it's going to mark you wrong. It wants you to stay consistent. So if they're using the variable t, you have to make sure you put t in your answer rather than x. Okay, so for forest B, I'm going to plug in 50, and I'm going to get 85 times 1.024 to the 50. Okay, I'm going to put those in on my calculator, and when I do that, for forest A, I get 313.769, and it says in the problem to round to the nearest tree, so I'm going to round up to 314 trees. For forest B, when I put that in my calculator, I get 278 and 2.238. And since we're supposed to round to the nearest tree, that's going to give me 278 trees. So after 50 years, forest A is still going to have more trees than forest B. But eventually, forest B is going to overtake forest A and start to grow faster and then get more trees eventually and surpass forest A.